So I want to thank everyone for sticking with us and welcome some new people into the workshop. This is the CIRI DHS Summer Research Team end of program research workshop, and we've had 3 presentations so far, and we're on our 4th and final. Our team this afternoon is from Northern Arizona University. We have with us Dr. Ho and his students, Manuel Lopez Jr. and Jimmy Devaney. And I'm going to butcher all the names, I'm sure. They are mentored by Dr. Al-Qaidi and, oh boy, here we go, Jingyu Liu from the University of Illinois. They are with us from the Illinois Center for Transportation. And Dr. Ho, you have the floor.
Thank you so much. Good afternoon, ladies and gentlemen. It is with the highest honor to present our collaboration project through CIRI's Summer Research Program. So today, our presentation topic is the integration of vehicle-based sensing and vehicle dynamic model for evaluating highway infrastructure resilience. I would like to start by introducing our team members. So I'm currently an associate professor in the Department of Civil Engineering, Environmental Engineering, and Construction Management at Northern Arizona University. Here today, we also have 2 students, and they are senior students in civil engineering and also environmental engineering majors. We have Jimmy Devaney and also Manuel Lopez Jr. And it is also our honor to be able to work with our mentor, Dr. Al-Qaidi from Illinois Center for Transportation, we call ICT, and also his doctoral student, Mr. Xiuyu Liu. All right, it's kind of introduction and also the background of this research. I just realized because our background is somewhat different. We are in civil engineering side with a focus on transportation. So we're trying to kind of slow down and explain as detailed as you can, so such that the audience today will better understand our research background. The first one I would like to talk about is called IRI, called International Roughness Index. IRI, for those of you who were not familiar with what IRI means, so IRI is an index, is a measure that's based on the measurement along a road profile. It is defined as an accumulated vertical displacement in a mile. So they say I put on a sensor in the vehicle and we travel along the freeways based on the 1 mile segment, based on how rough the road or how bumpy the road. So we collected those vertical displacement. That's why we get output. So as you can see, the higher IRI means the rougher the highway surface would be. So when you travel through the highway where the IRI value is very high, you will feel very bumpy experience. So it's not very comfortable traveling through those highway where the IRI is very high. So IRI is a very important measure of pavement rideability, and also it is an international standard where those highway agency, for example, Federal Highway Administrations, or we have each state Department of Transportation, they all use IRI to give them a better idea if their highway pavement needs to be repaired. Now, what I would say, the current IRI has been introduced by the World Bank organization back in 1980s. It's been a while, almost 40 years, 4 decades, and it's a theoretical model is based on quarter car. So that's only one quarter car model where it was developed. So for the 40 years, that entire model has not been updated. So that's a big challenge we are facing right now. So as soon as we get awarded this summer program, we got an opportunity to work with Dr. Elkadi, also his research team, Mr. Xiuyu Liu. So we kind of exchange our research idea to see how we can better collaborate each other using our individual research expertise. So we come up is, all right, because we have been collecting vibration data on the I-10 corridors in the Phoenix area. I-10 corridor is very important freeway segment because that one start from California all the way through to Texas. So many heavy trucks, semi trailers. So the road in our area is very bad. It's very bad. Now, so far, the IRI on this guy right here uh, is collected using a truck called Highway Profiler. It's very, very expensive. I went to a conference exhibition. I asked the salesperson to see, hey, how much cost of your Highway Profiler? And he said approximately $300,000, including everything, including the vehicle. So it's very expensive. So it is not a ideal for most of government agency, like our city, our county government. They say it's not affordable for them, especially where their budget is very limited. So in the past, we used another alternative method to collect vibration data, which we call vehicle-mounted sensor. Is we develop our sensors. Our sensor. We put a sensor box or longer on the control arm of each tire. And each sensor box is approximately only like $250. You can put everything together. So it's considered a cost-effective way to collect vibration data. So this is what we've been doing right now on our side. Also, when I spoke the research program with Dr. Elkadi, he said, yeah, recently his research team have been developing a four-car model, the entire thing, four-car model with a 7 degrees of freedom. And so we first find out this is a very excellent opportunity for both of us to use our devices, our research interests, and we come up together to further develop a research tool called integrated system using vehicle-mounted sensor and a four-car model to validate the pavement roughness, also predict pavement roughness. So that's our idea and at very beginning. All right. So far I would like to introduce why we have to use a vehicle mounted sensor, right? It's kind of background. So far, when we look at transportation area, there's two methods which are considered affordable to collect vibration data along freeways. The first one is right here called smartphone embedded accelerometer. So you just download app into the cell phone and put a cell phone on top of dashboard and you travel through any roadway and you collect sensor, collect vibration data. Another one is like what we've been doing right now is we use vehicle-based sensing method. We put our sensor logger on top of control arm and travel through. Now, I would like to highlight because smartphone sensing method, it is still not adopted by highway agencies. The drawbacks is we cannot calibrate, we cannot repair, we cannot program those mobile apps. Once you download, that's it, right? We don't have any capability to develop or to fix. So that's why this one vehicle-based sensor is better way because we can design our sensor based on our need. Right? Can calibrate and add, upgrade any devices, any chips. So that's we consider this as a better way to collect vibration data. So after understanding our individual research interest, that's why we both sides, Northern Arizona University and also University Center for Transportation. I spoke to Dr. Elkadi. We both agree. Now let's put together our research interest and trying to address a long-term issue, which is quarter car model limitation. And also would like to propose this integrated system of vehicle mounted accelerometer and also full car model to predict IRI. So that's our objectives. All right. So the first thing, because we never done it before, so we don't even know where to start. So while we at the very beginning, we asked Arizona Department of Transportation to give us the IRI data. So they sent us the IRI data. That was recorded in 2019. So we even know, okay, how do we match our vibration data into IRI? So we spent quite a few time trying to figure out how can we better match our vibration data into it. So I would like to ask one of our students to kind of share what they would what they did in this methodology. So I would like to ask Manuel Lopez to jump in to this slide.
Thank you, Dr. Hu. I guess to recap on our project here and our research, we took two segments along the I-10 corridor here in Phoenix, Arizona. One being westbound, eastbound from 27th Avenue to 51st Avenue, and the second being from Baseline Road to Chandler Boulevard. The segment I will be focusing on in this slide will be the Baseline Road to Chandler Boulevard. Our methodology included using GIS software, which is a geospatial referencing tool. It's heavily used in the civil engineering community as a mapping software. It has a lot of good applications. We thought it was very integrated for our research, and from that we were able to pull data and do numerical analysis. So through GIS, when we connected the sensors to the vehicle, it drove along the northbound, southbound route here shown in the map, and it registered the points. Each point that it registered, which was an acceleration point, it had an associated latitude and longitudinal coordinate with it. That allows us to pull that data into GIS, which we're able to kind of differentiate different features and elements of from data through Excel. And we're able to highlight those points and get them accurately placed into a mapping software, which is what we used. And then through the ADOT files that we received, the IRI data for 2019 also had latitude and longitudinal points. So we're able to pull those points into GIS as well, kind of mix around with the different points, and we're able to manipulate what we want to see as far as the different features. So the features that we were most interested in were the average IRI. So for our research purposes, we kind of broke it down into IRI categories: good, fair, poor, and severe, with ranges going from 0 to 69. Anything below 70 is considered a good IRI value. That means your pavement is in good condition. Anywhere from 70 to 135, that is considered poor. There's a little bit of wear and tear. Anything over 135, that is poor, is severe. That might indicate some cracking, either longitudinal or transverse, which is could be different kinds of cracking going along the pavement highway. So if you look at my exhibit here on the map, you'll notice a lot of green points. That could be there could be a number of factors that go into when analyzing this segment of roadway. There could have been recently some chip sealing, some crack sealing. A lot of the federal highway agencies, they do have rehabilitation schedules put in place for all the highway systems. So this one might have been freshly coated, so that's probably why we're not seeing a whole lot of cracking, severe pavement, or even poor or good. We have a lot of good condition right here. So when going through the analysis, we noticed some of the initial data that we were pulling had some discrepancies. It wasn't lining up correctly with IRI versus the acceleration points that we were seeing, because the whole point behind our method was to gather the acceleration points and see the vertical acceleration, which is the responses that those tires are experiencing along the highway, and see its relationship to the IRI. An observation that we made about a couple weeks in was we noticed that our vehicle was front wheel drive. So we were at the beginning taking in averages and taking vertical acceleration points from all four tires. But when dealing with a front wheel drive tire, those front two tires are going to, have different responses than the back two. So we decided to shift our focuses to the front wheel tires. We started focusing more on those acceleration points and seeing how those tires behaved in those vertical responses. And we would the numerical analysis behind that was taking those acceleration points, finding the averages of the points along a designated point. So right here in my graphic, I show some of the various points that I chose through object ID, and I showed their IRI value next to them. Taking random selections and choosing acceleration points that had the closest or that were on top of an IRI data selection point. From there, we gather the averages of the tires. So we take the mean average of the front front tires together, and we try to see what kind of acceleration points they have and relates to the IRI. So if you notice, when we go through the graph section, we were able to put together and find a correlation between the vertical acceleration and the IRI with an explanation coefficient of roughly 8.86 for my segment. Altogether, I think we were able to come up with an explanation coefficient, or R squared value, of above 0.85, which shows strong correlation. So to recap, or to go a little bit further, I'll pass it on to my colleague here who can explain the eastbound westbound segment. Jimmy.
All right. Hello. Thank you, Manuel. So I did the eastbound westbound segment, as Manuel said. And so he went into a lot of the background. So I'll kind of explain our process in a little bit. So what we did here is, what you can see is all these green points on the left are our differing IRI points that we got from ADOT. So the bigger the symbol basically means it's a higher IRI, or that it's a problematic segment of the freeway. And all those tiny little darker green dots throughout are our vibration data. So even just from this graphic, you can see we gathered a lot more data points than the standard IRI method does. It gathers roughly about 200 to 300 points more per IRI point than current methods. So it can be a lot more accurate. But what we did, because we had, we're looking at roughly 100 points or 200 points per IRI point, we would take the average. We would encompass kind of all those vibration data that we gathered around a singular IRI point. And we would take an average of those and try and see, okay, is our ZG value, and when I say ZG, I'm talking about acceleration or our vibration data. When our ZG value is high, is our IRI data point also high? Meaning that would kind of prove that our data collection method is accurate. And so as you can see on the graph on the right, what we did then was, once we gathered enough points and we kind of put them all together, we said, okay, with this RI point with 103, what was the ZG value, and was it consistent over a long period of time? So I put them together in a graph here, as did Manuel, and you can see we had another correlation coefficient pretty high, around 0.8, demonstrating that this data was pretty accurate and showed that this was a good method to collect that data. And so, yeah, with both those together, we eventually put them together and stuff too, and we found another higher R squared value. But yeah, so that was kind of the basic process, and I'll pass back to Dr. Ho to finish up. Thank you.
Thank you, Manuel. Thank you, Jimmy. So we spent the first couple of weeks trying to figure out how do we better correlate with our vibration data with IRI, especially the IRI that was collected in 2019. However, because our vibration data were collected during the March of 2017 to the February 2018, so we thought it would be better that if Ada can give us another data set and that actually is in 2017, so we can actually compare the accuracy of our data matching with IRI data. So we made another request to Arizona Department of Transportation. So that's why we said ADOT. So ADA sent us back with IRI data in 2017. So because we spent quite a few time trying to match our vibration data with IRI in 2019. So as soon as we get IRI data in 2017, so we were able to follow the same process, trying to find out again the correlation between our vibration data and also IRI, both from that's we say eastbound, westbound, and that's called northbound, southbound. So that's kind of big layout of where our vibration data were collected. And this time, the lesson we learned from very beginning is how do we can better select a data point where we can reduce our time, because we realized at the very beginning we spend a lot of time. Also, we learn something that we might also come up with the data which was not very accurate. So when we move to compare our data with 2017, we use a method called winter interpolation method to help us better match our data and also better make us a better selection. So what we do is right here. So if this is IRI data, so that's what you see different legend right here. If that's IRI data with the green color symbol, and then we consider as a very poor condition. So what we do is we kind of use this point as a base point and make a selection window, like the selection window. So we reach about 30 to 50 point on each side, left side, right side. And then we select those acceleration point and average to get our vibration data and that correspond to this IRI. So that's what we did when we do the second round of data matching and also selection. So we use window interpolation method, which can help us significantly reduce time and saving. So here's the result that we got. So this is based on IRI data in 2017. That's based on our acceleration of gravity, which is the ZG value that we mentioned. So as we can see right here, this is eastbound, westbound, and there's a northbound, southbound. And also the R-square value that we get is both on between, say, 0.8 to 0.85. We also put these two together, these two corridors together, and you will get even better R-square value that will increase to 0.89 from 0.85. So at this moment, we feel confident. Right now, our data can better match the IRI data. So the next step is we run dynamic model. Because this model is developed by Dr. El Khadi and also his PhD student, Mr. Xiuyu Liu. So Mr. Xiuyu Liu is using his model, and the model I mentioned is right this one. So this called four-car model. This four-car model is they need the input from IRI data. Based on the IRI data, they can predict different magnitude of roadway condition. For example, this the output is in a acceleration unit. And then we can do integral convert into a velocity and do another integral convert into vertical displacement. So this This graph demonstrates the capability of full-car model for roadway roughness predictions. So as soon as we finish our data matching, we forward our data to Dr. Elkati and also his team. And Mr. Xu Liu was able to run his numerical analysis, and that's why the result he came out. So if you look at right here, this is our data measurement. And you see it in red color. On the horizontal axis right here, this is basically that's a roadway roughness based on IRI input. So we both compare together and we find out the correlation coefficient between our field measurement and also the simulation. The simulation is about 0.9, which is very close, very close. So that's why we find out our field data is in a good agreement with a vehicle dynamic simulation. So that's why we were very confident that this integrated system that consists a vehicle-based sensing and also a full car model can accurately predict roadway roughness conditions. So here's a conclusion of our research project is the vibration data collected from our vehicle sensing could be a very good representation of actual pavement responses. Like I mentioned, we can use cell phone accelerometer to collect vibration data. We can also use our vehicle-based sensor to collect vibration data. But as you compare both, we see based on this research, we find out and our vehicle-mounted sensor is better and also can get a very good representation of actual pavement responses. We also find out the full car model that developed by our mentor, Dr. Elkati, and also his co-workers, is their data has been successfully used to validate the field data. So this is also a very good indication that their full car model is capable of predicting roadway roughness. So the results based on this project and show this the integration of our vehicle sensing method along with a full car model could successfully predict pavement roughness. So I would also to conclude that based on the past every 9 weeks research team, we has been able to prepare a paper we submitted to the Transportation Research Board. So now that paper is under review right now. So like I say, we both agree we never done very short of time to get together and also submit a research paper. So the experience we thought is very amazing for us, especially for students who never had that research experience before. So we're very happy about the result. This acknowledgement is we appreciate the research is funded by the U.S. Department of Homeland Security Department. Now this Q&A. Thank you for listening.
I mentioned in the chat that if you have questions, you can either put them in the chat or you can raise your hand. You do actually have a question from one of your fellow students. Jared asks, how many different vehicles did you use to record your data on?
Let me switch. So actually, we use only one vehicle because to be consistent. So we use 2016 Honda Accord, so such that we can minimize any like uncertain factor. For example, different tire, different damping systems. So we only use one for data collection.
And then Jared has a follow-up. He asks, in the future, do you plan on trying different vehicles like sedans or trucks or other means of transportation?
We do. At the very beginning, we try to use different like vehicle, for example, pickup truck, even though different size of vehicle, like sedan, even SUV. So it is possible for any in the future that we use different type of vehicle to collect data such that we can compare how those vehicle vibration responses look like.
I had a quick question and then a follow-up question, if that's okay.
Sure, go ahead.
Yeah, first I wanted to ask, have y'all tried this on any other kinds of roads besides just paved roads? And, you know, this isn't my second question. Do you think that there would be anything that could be gained from trying this out on, you know, maybe like gravel roads or other areas like that? And then second follow-up question, if you haven't or if you have tried that data, do you think that that might be good for information gathering purposes, right? By being able to tell which areas might be more well-traveled than other areas? Right, by being able to dictate or by being able to tell like, hey, this area is a lot smoother, maybe there's more vehicles running over this, or, you know, I don't know as much about it, but I was just wondering because it seemed like there might be other applications to this as well.
Yes, it is. I did in the past, like 2019, before pandemic, we used the same method. We put our sensor into a pickup truck and we travel through those unpaved road in our national forest road. So it is applicable to use the same method on different type of road, like unpaved, even though they can put like asphalt, concrete, stuff like that. Yeah, that you can use that road for those different type of pavement conditions as well. And same thing, based on the vibration responses, we should be able to identify. At this moment, we cannot really tell in terms of volume, traffic volume. Let's say this road might be traveled by the amount of traffic. So we cannot judge at this moment. But the only thing we can do is based on vibration responses, we are able to make decision to see if that road in that area that needs to be repaired, and such that the highway agency can prioritize their need for, like, say, overlay or for that construction, stuff like that.
Yeah, Kian's got a question before mine, but I had kind of a follow-up question, but I'll let you answer his first. Sorry.
All right, I didn't get message.
Oh, it's in the chat.
Yeah, Kian asked, and I'm going to add to this too. Jared also mentioned that suspension and shocks, let's say on a Jeep or a Kia Soul, would be very different. So I guess that's why he was asking his question about sedans versus trucks, etc. So I don't know if that was kind of answered. But then also Kian asks, was tire pressure normalized during this process, or would its effects have been negligible?
For damping, of course, this is part of the coefficient factors that will influence our output, because this model is actually developed by Dr. L. Carney's student, Dr. Xu Liu. I don't know if Xu Yu would like to kind of answer the questions.
I'm sorry, the question is, during the development of the vehicle model, whether the different types of the vehicles or the different tire inflation pressures has considered in my research. Is that correct?
Correct.
Okay, so answer is no. We just choose like normalized tire inflation pressure because basically the tire inflation pressure will affect two parameters in my model: the tire stiffness and the tire damping. And when we are developing the full vehicle model, we choose like the parameters that we think will be like most representative of like the average inflation pressure in the market. So we didn't choose different tire inflation pressure, but in part of the research, we did some sensitivity analysis to show the influence of tire stiffness and tire damping on the predicted vehicle accelerations and other responses. Yes, that's my answer.
Okay, and then kind of to follow that up, Max, we'll let you ask your question in a minute. Also, to the same points, what about weather conditions? Does that affect the results? And then also, Jared is also asking about driving styles too. Another interesting question.
Yes, Weather condition does have a significant impact on the vibration responses because the data we collected is based on year-round. Like I mentioned, is from March of 2017 to the following February 2018. So it is a year-long data. So we also measure the pavement temperatures when we do vibration collection. So we find out, but we don't collect data where it get rains. So that's the only thing I need to mention. But for the temperature wide, it is, we find out during summertime, like say July, August, September, even though June, the vibration responses get higher than the rest of time. So it does have a significant impact. And also driving style, of course, it will change. Because you cannot accelerate your vehicle, and also reduce. So to reduce those uncertainty factors, what we did is we collect data at midnight, where the freeway get no traffic or get less traffic, so we can maintain our vehicle speed as stable as 60 miles per hour. So around 60 to 65, that's the driving speed that we were trying to maintain when we collect data. So that's why we choose midnight, not rush hour. If rush hour in Phoenix area, it is impossible to collect vibration data.
That's really interesting. Max, go ahead.
Yeah, I was just wondering whether y'all had considered incorporating like image recognition, along with the data that you were using, just to see, hey, maybe there is a correlation between how the roads appear, right, and the roughness that we're seeing. Because I figure that would be really good both for identifying roads that would need repair, and again, going along that like reconnaissance or intelligence route. It'd be interesting to see if there was a way to be able to detect common ways that are driven down that might be like unmarked roads or something like that. Again, by detecting roughness that's going on and maybe the appearance of the surrounding area. But I was just thinking, this is really interesting to me, this particular topic. I apologize.
No problem. Yeah, I mean, indeed, that's a very good question. So what I can tell you is before we collect data, we do attach a GoPro on the back of our vehicle. So that's why we can collect vibration data as long as imaging. So we do have a video that corresponds to each vibration data collection. So like I say, on the map, we can identify those severe point locations. So when we go back to see, okay, if I would like to see what exactly those pothole or big crack looks like, we can use our the video, the film that we did to actually visualize their roadway conditions. So Max, yeah, you did ask a very good question on that. And also imaging process will be an also ideal way to actually capture that crack condition, right, in the real time. So that could be connected with our vibration data too. So that would be the research idea. You're trying to, how do we integrate the imaging processing through our vibration data, and to get a better idea, also indication to see, okay, where the road looks bad. So that's a very good research interest too.
I think just to add on to that point, the software that we used, GIS, does allow some features where you're able to take snapshot real-time photos. That was, we were driving along, and you're able to associate those photos with the point that it collected. So along with the latitudinal and longitudinal points, you're able to see the process picture that snapshots were able to confirm some of those critical cracking locations, which is what we used, what we did to look at some of those high RI value points and see what our vertical acceleration data look like. And we wanted to see the picture, so we're able to kind of make those connections and use different features and tools within GIS to kind of make those connections. And then I think someone also asked about applications for this method. Some of the ones that we kind of went through, it could be used for pavement rehabilitation, pavement preservation, and also pavement planning. A lot of the agencies like ADOT, Maricopa, City of Phoenix, or local municipalities from where you're from, they do already do transportation planning with regard to how they're going to preserve their pavement and how they're going to preserve their roadways. A lot of the process that they do right now is very costly. So our method and our goal was to develop a cost-effective and efficient way to predict those pavement roughness, so that we're able to identify cracking locations, and maybe hopefully, like I said, an application would be to predict pavement roughness and pavement conditions to allow for pavement planning.
Yeah, thank you, Manuel. That's a good point, because our goal is to provide a cost-effective, it's not costly method that at least each government can afford to use this method to predict their pavement conditions. I don't know if
Are there any further questions? Oh, wait. Dr. Kim just put something in there.
Okay.
It seems related to vehicle safety issue. One question about the content of this research. Just wondering, what is the linkage between this type of research and the security mission of DHS? That's a good question.
Because when we first studied that program, we want to focus on infrastructure. Of course, infrastructure is very broad definition, so we really want to focus on highway infrastructures, trying to provide a better idea to predict pavement roughness. Like I say, so that's why the first one will see how do we better improve our nation's infrastructure by using a cost-effective method and tool that is affordable for most of highway agencies. So that's our goal that we are hoping to achieve through this program.
I think you answered his question. Great.
Thank you.
You're welcome. Does anyone else have any other questions? See, Randy.
Yeah, this is Randy.
Yeah.
It's not really a question, but I would love to see you guys run your test in Chicago in late winter. You talked about potholes. I'd love to see if your sensors could survive the mother of all potholes in Chicago.
We'll try. We can put a
I doubt
research
it.
idea.
I don't think the vehicle will survive, much less your sensor. Great presentation. I really appreciate it. It's very interesting work.
Thank you.
Looks like Max might have one more question.
Yeah, I'm sorry. I'm just full of questions today. I was wondering, in regards to the software that y'all were using to do a lot of this analysis, whether you were using any open source software, and if so, again, as I'd mentioned in the chat, I have a couple of books on Python libraries, whether y'all use any specific libraries that might be interesting to, utilize for future projects for ourselves.
Of course, in this project, we only use ArcGIS. So we use ArcGIS to can do mapping and also programming. We don't use Python. Okay. But I know Python is a very helpful tool, and hopefully we can bring this one into our future research as well. Another research project also is actually, I asked my student to learn Python and how to use Python to help us better retrieve data. So it is definitely a good tool for research. Yeah.
Max is offering for PDFs to send them to you guys. And I'm happy to share. Well, you guys have been on a lot of emails together. Right? I don't need to share emails, but if you need me to, I'm happy to do that.
Sure.
Yeah. Well, Jordan has a question. Go ahead, Jordan.
If we don't have time, it's okay.
No, it's fine, Jordan.
Okay.
Go ahead.
I don't. Just a question. Pardon me if I don't use the right language here. Does this have any with monitoring kind of pavement structure and kind of how smooth it? Does this have anything to do with like exploring? I guess being in the Southwest, since you collect your data in Phoenix, is it just highway or like at intersections where you get the the wave effect. I don't know, being in the Southwest, you might be able to speak to this or understand what happens in intersections where it becomes very wavy because of the constant stopping and starting. Is there application there, or is that not really the focus of where you are for the research?
Before I answer that, Manuel, do you have any like experience? Because Manuel worked for our like agency, government agency for a while. So did you have any experience for this one before? Maybe want to share?
I will say, so how intersections, or what we call them as major arterials and minor arterials, which is the general pedestrian streets that you drive on, are treated very differently from major highway systems. So I think this application, this research would be more geared towards major highway, because you are getting those constant tire pressures, those constant responses. But like we kind of iterated through the presentation, vehicle type, drivetrain, they are all factors in what causes different roadway roughness, and whatever will cause a different impact. So obviously, a small sedan car is going to have a different impact versus a large truck trailer. So the way intersections are usually treated is, they'll kind of put it on a pavement schedule or pavement rehabilitation schedule. So sometimes those intersections get treated every 3 to 5 years. I just kind of know locally here in Phoenix, it's usually 3 to 5 years. They'll take a look at it. They'll take core samplings. They'll drill a hole and take a sample of the pavement and the soil foundation below it, test it, kind of see how it's going, and they'll go from there. So to answer the question, I think this research was more geared towards major highway design and major highway pavement condition.
No problem. Just wondering if there's any application there, but thank you so much. Appreciate it.
Thank you, Manuel.
Okay, we're at the end of time, and I just want to thank all of our students and all of our faculty. And I don't know that I'll get to quote unquote see you all before the end of the week and the end of our program. But I just want to reiterate to you guys, if there is anything that CIRI, myself, Randy, Katie, and the rest of our CIRI team can do for you, please do not hesitate to ask. We are available beyond this program. We have frequently written letters of recommendation, etc., and would love to continue to hear from you in your endeavors, your future, your jobs, and everything else as well. So please keep in touch. And I want to thank everyone who joined us today and made it through the whole thing. We really appreciate your time. And I think I said this at the beginning, I wish we could all be in person rather than virtual, but I think it worked out okay. Thank you all very much.